Good afternoon. Welcome to Krishna's classroom. I wanted to revisit L infinity E. In fact, we discussed it in the episode number 71, but I thought that there was some lack of clarity and also possibly some mess up with the notations. And therefore, I thought I would do it for the sake of clarity again. Now, therefore, I have numbered this talk as Lebesgue integration theory 71A. Okay, so let us recall what L infinity is, be clear about what it is, and also about the notations. Now, we had E as a measurable subset of R. Then we looked at all F, A, a real valued function on. Then we introduced the following identification. This is the relation for almost all x. And this is an equivalence relation on the class all now we have, so therefore it induces a partition. And let this is our notation. The equivalence class of all functions. The above equivalence relation. Then a typical element of designated by which is defined as the set of all G such that G is so these are the elements of a typical element of F tilde. So we define L infinity. So we define before that essential boundaries. F belonging to said to be essentially bounded. He essentially bounded on E provided there exists some M positive or non-negative for which for almost that's the definition of essential boundaries. Now we define for which then one can easily the L infinity, or in fact we have seen it earlier, a linear space. So this is first. Now what we do next is to make it a normally linear space. So this is quite easy to prove. You take two elements. Now you see that this is the sum is defined as the equivalence classes or the class of all functions is equivalent to fg, and this is well defined. So also that's the addition and scalar multiplication. That's how it is defined. Now you can show that this is well defined. This is defined, and then you see that if you define f plus g, is that f comma e, and for every alpha belonging to R. Now therefore this is a linear space. Now we define a norm on this. So let us define this. The norm of f is defined as infimum of the essential upper bounds of f. Essential upper bound is a m positive or m non-negative such that almost everywhere. This is the m. So you have got several such upper bounds, and you know that it is bounded below by 0. Therefore, the infimum exists. Okay. Therefore, this is well defined. I mean, you can show that it is well defined. Use some other g for it, it's the same. And we shall prove this. Now, if f is g, then g and and the essential supremum of they differ only on a set of measure 0. Okay. Now the claim that we make is this. That is the main thing. So let us first prove this. This is equal to 0, which happens if and only if essential supremum over E of F equal to 0, which is if and only if Fx equal to 0 for almost all belonging. That is if and only if this is the 0 element, or this is the 0 function, or the 0 element of this is the in fact the 0 element is the equivalence class of all functions which are 0 almost everywhere. Okay, therefore this is there's nothing to do. Now we establish the triangular integral. So that talks about the positive. Second is triangular integral. That is, we want to prove this. Now we claim is an essential upper bound for F that's a claim. Once we prove that, the triangular inequality immediately falls. Because of the infimum and supremum and all these things are coming together, it's a little bit of explanation. And I think when I introduced this in the last lecture, there was some hasty statement that I made, and probably which went into, which directed into some confusion. So I wanted to clear that. Okay. That is, we want to show that this is what we want. This is a statement. Let's prove this. Now, for each n, a positive integer, there exists a en designated by en of e such that mod f almost everywhere. So this is the statement that comes from the infimum of the supremum. Okay. Therefore, let us write down the details of that. So En has measure 0. Now measure of means on, see, I am using a schematic diagram. This is let's be precise, on E/n with measure of En 0. So measure of En is something which is 0. So this is E/. Now one can easily see the relationship between En and En plus 1, so on. Hence, if we define E infinity to be equal to En, then we have mod f is less than or equal to on infinity. and we have measure of because it's a countable union of measurable sets, each of measure 0. Okay, so that this is the definition. Okay. So we have essentially proved what we wanted to prove. Thus, what we have is the following. The essential supremum of F is the smallest essential upper bound for F. Which implies now we shall use this to prove the inequality. For F we have fx plus this is less than or equal to and this is less than or equal to, now this one is less than or equal to almost and that implies next step is an essential upper bound essential upper bound for f plus g, and hence what we have is this. Which is less than or equal to now that completes the proof. Triangular integral. What next? Next we prove the positive form. Third property. This is positive. This is the positive. Positive. That is now this is just one line. Let's prove this. So let us work on this. Infinity is essentially t, and this is equal to mod alpha into exactly that. This is true for every so that completes the proof of it. Now what we do next is we want to work on. Thus we have seen that that L1 and L infinity are normed spaces. So it remains to show that LPE for 1 less than p less than infinity are spaces. This we shall take up. Supporting results. We shall take it up. Take it. So thank you very much. So that completes our. I'll wind up here for today's short talk.